In single variable calculus, we often evaluate integrals using the fundamental theorem of calculus. So the fundamental theorem says that if f of x is a continuous function and there exists an antiderivative, we'll call that capital F of x, so that the derivative of capital F is little f on the interval from a to b, then we can evaluate an integral from a to b of f of x dx by finding that antiderivative capital F and evaluating it at the two endpoints and finding the difference. So the integral from a to b of little f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. So essentially, what we had is that we could evaluate this integral if we had some sort of notion of the antiderivative, and then we evaluate that antiderivative at the boundaries of this interval, a and b. So in multivariable calculus, there are going to be several different notions of the fundamental theorem of calculus, but all of them are going to revolve on having an antiderivative and then being able to evaluate that antiderivative on a boundary. The first instance in which this comes up is the fundamental theorem for line integrals. So we will discuss in this lesson the fundamental theorem for line integrals and then also independence of path. So I'm going to illustrate this by starting with an example. We're going to let C1 be the line segment that connects the points between 1, 0 and 0, 2. So that will be this line segment here. And then C2 is going to be a parabolic path that connects the points 1, 0 and 0, 2. So that path is going to be given by x equals t and y equals negative 2t squared plus 2. That gives us the parabola y equals negative 2x squared plus 2. That'll be our curve C2. And what we want to do is we want to evaluate a line integral of the vector field xy dot dr over the two different paths C1 and C2. So let's start with C1. C1 is going to be the line segment. So we need to have the initial point. That point's going to be 1, 0. And then we're going to have t times the vector that points from 1, 0 to 0, 2. That vector is going to be negative 1, 2. So we can write this, if you like, as 1 minus t and then 2t. And here we're thinking about t as being between 0 and 1. Because at t equals 0, this line segment starts at 0, 1, or 1, 0, and then at t equals 2, it ends at, at t equals 1, it ends at 0, 2. So x in this case is 1 minus t, and y is 2t. Now, to evaluate the integral, we're going to need r prime of t. That's going to be negative 1, 2. So that's the direction of that line segment. Okay, well, we're going to want to integrate over C1 f dot dr. And so f is just a vector field x comma y. So x is 1 minus t y is 2t. So we want to integrate that from 0 to 1, and we're going to dot that with r prime, which is negative 1, 2. We want to integrate dt. Well, if we perform the dot product, that's the integral from 0 to 1 of negative 1 plus t plus 4t. So we're going to integrate from 0 to 1 the function 5t minus 1 dt. Finding an antiderivative, we get 5 halves t squared minus t evaluated between 0 and 1. There's that fundamental theorem of calculus that we're applying that allows us to evaluate this integral by evaluating the antiderivative at the endpoints. We get 5 halves minus 1 minus 0, and that will give us a value of 3 halves for that line integral. Now we want to try C2. That's the parabolic path that goes from 1, 0 to 0, 2. And so I gave the parabolic path, so this is r of t in this case, as being t and the negative 2t squared plus 2. But hopefully you'll notice that it's actually at t equals 1 that this path starts at the point 1, 0. And then it's at t equals 0 that the path ends up at 0, 2. So we're actually going to start this integral at 1, and then we're going to end at 0, so that we're going from the point 1, 0 to the point 0, 2. So here again, x is t, y is negative 2t squared plus 2. Okay. We want to evaluate, or we want to find the derivative, r prime of t. The derivative there is going to be 1 and then minus 4t. And so we're going to evaluate this integral over C2 of f dot dr. So f, again, remember, is just xy. So that's going to be t negative 2t squared plus 2. That gets dotted with r prime, which is 1, and then negative 4t. And then this integral is actually going to go from 1 to 0. Again, so that I start at the point 1, 0, and I end at the point 0, 2. Okay, so I'm going to integrate that dt. We're going to multiply this out. So this will be the integral from 1 to 0 of, let's see, t times 1 is t. And then negative 4t times negative 2t squared is an 8t cubed. And then we're going to get a minus 8t. We're going to integrate that dt. Okay, so I don't like integrals that go from a larger number to a smaller number, so I'm going to rewrite this as minus the integral from 0 to 1. And then we're going to be integrating 8t cubed minus 7t dt. So we need to find antiderivatives. So this will be minus, and this will be a 4t squared. Actually, take that back. This will be a 2t to the 4th. And then minus 7 halves t squared, evaluated between 0 and 1. So I'm going to get a minus 2 minus 7 halves. minus 0, of course. And so 2 minus 7 halves is negative 3 halves. So taking the negative, I get, again, 3 halves. And then this is curious because in our previous lesson, we saw that when you integrate a vector field over different paths, that you're likely going to get different results. But in this case, we integrated this vector field over 2 different paths, and we got the same result. And the question is that a coincidence, or is there something special about that vector field so that when I integrate over different paths, it still gives me the same result? So that leads us to our definition of path independence. Okay? So our definition is that the line integral of f dot dr is independent of path in a region we'll call D, that's a 2-dimensional region, provided that given any 2 points A and B in that region, the integral has the same value along every piecewise smooth curve or path from A to B in D. In this case, we can write the integral of f dot dr as really being the integral from A to B, because the value of the integral depends only on the points A and B and not on the particular path that joins them, that path being C. So this integral that we just did in this example appears to be path independent. Now, we're not exactly sure. We would have to check all possible paths from the point 1, 0 to 0, 2. But checking along 2 different paths, we did get the same value. I can tell you with confidence that that integral actually is path independent, and we'll be able to show that with what we're going to learn in this lesson. But for now, we're going to define an integral to be path independent if the integral really only depends on the starting and the ending points, but not the path that you take to get from the starting point to the ending point. So this path independence is going to be important for us understanding how we can evaluate certain kinds of line integrals. Okay, let's continue on to the fundamental theorem for line integrals. The fundamental theorem for line integrals says let f be a function of 2 or 3 variables, and let c be a smooth curve that's parameterized by the vector valued function r of t, where t is between a and b. If f is continuously differentiable at each point of c, then the integral of the gradient of f dot dr is equal to f of r of b minus f of r of a. Well, there's a lot of information that's in here. But basically, this is very similar to the fundamental theorem of calculus that I mentioned before. Specifically, it says that f has to be continuously differentiable. Okay? Well, in this case, little f is the function that's going to be serving as our antiderivative. And then we want to integrate the derivative of f. So first of all, we have to be able to take derivatives. So we're going to integrate the derivative of f here. So it's almost like we're integrating f prime of x dx from a to b. And we need what's inside there to be continuous. Okay, so in this case, we need f to be continuously differentiable, meaning that all the partial derivatives of f are continuous. Okay, so what's inside the integral needs to be continuous. So I see a derivative, okay, and then we're going to integrate that derivative. And then how do we integrate the derivative? We integrate that by evaluating the antiderivative, which in this case would be f, at the points B and A and finding the difference. So here, notice that I've evaluated f at the endpoints R of B and R of A, just like before. So this really is the fundamental theorem now for a line integral, but the line integral has to be over a vector field. That vector field has to be the gradient of some function f. Okay, so if in that case, if f has to be the gradient, or sorry, if we're going to integrate the gradient of some function f as our vector field, right, then this vector field, we'll notice, is conservative because it's the gradient of a function f. What do we call that function? We call that function a potential function. So we're going to evaluate this potential function at the endpoints. And so the potential function is kind of like our antiderivative. Okay, it actually isn't too hard to show that this is going to be true. Okay, we want to integrate the gradient of f dot dr okay, and then the way that we can do that is use our definition of how to evaluate these line integrals. So we would integrate over the path r of t from a to b. Okay, and then we would integrate the gradient of f, so that's my vector field, evaluated at r of t, dot r prime of t dt. But in fact, this expression should look familiar because that expression is exactly the right-hand side of the chain rule. So we can rewrite this as the derivative of f of r of t. So what we've done is we have essentially reversed the chain rule. Okay, what's on the right is generally what we think of as being on the left of the chain rule, the derivative of f of r of t. And then what's on the left is the expression of that chain rule, gradient of f of r of t dot r prime of t. Okay, well now what you should realize is this right here, this is a single variable integral. This is something we've done before. Okay, we have encountered these before. We can evaluate single variable integrals using the fundamental theorem of calculus, right? So the integral of the derivative of the function is going to be just the function itself. It's f of, okay, we got to evaluate it at t, so f of r of b minus f of r of a. Okay, so by the fundamental theorem of calculus. And so it actually isn't too hard to show that if you integrate the gradient of a function, okay, dot dr, that in fact you can evaluate that integral just by using the endpoints. Aha, so that says something about path independence there. This integral must be path independent because now all I need is the values of my function at the endpoints. Okay, a fun little corollary of this is if we let C be a closed curve in D, then if you do the integral around a closed curve of the gradient of f dot dr, it must be 0. And we know that it must be 0 because in this case, right, we're going to get that the starting point f of r of b minus f of r of a, the starting point and the end point must be the same if we're going around a closed loop. And so in that sense, they're going to be equal. So these 2 points here are going to be the same point. So if you have a curve that starts and ends at the same point, making a closed loop, and then you integrate the gradient of f dot dr, you're going to get 0. So in the next part of this video, we'll talk about how this relates to path independence and conservative vector fields.